millions of people flock to snow parks and ski resorts to experience the pure thrill of tubing down perfectly sculpted snowy hills. Laughing crowds, spinning inflatable tubes, and endless white slopes create the illusion of a natural winter wonderland. But what most people never realize is that these smooth, safe, and thrilling tubing hills are not created by nature alone. They are engineered masterpieces, shaped by colossal machines, advanced technology, and a highly coordinated grooming process, carried out with scientific precision. This is not simply snow piling up and people sliding down a hill. This is the supergiant snow grooming process. A massive operation where thousands of tons of snow are collected, redistributed, compacted, and sculpted into flawless tubing lanes designed for maximum fun and maximum safety. And before we dive into this breathtaking transformation, make sure to like, subscribe, and hit the bell, because what you're about to witness will change the way you see snowy hills forever. Snow tubing has evolved from a simple playful activity into a billion-dollar winter recreation industry. In the early days, children used makeshift sleds and inner tubes to slide down natural hills after heavy snowfall. But as winter tourism expanded, resorts realized the demand for controlled, safe, and repeatable tubing experiences. This gave rise to purpose-built tubing parks across America, particularly in colder states such as Colorado, Vermont, Utah, Pennsylvania, Michigan, and New York. These facilities feature dedicated tubing slopes, conveyor lifts, lighting systems, and fully engineered snow surfaces. Unlike natural snow hills, modern tubing terrain must meet strict safety standards, ensure consistent speed, and provide optimal surface conditions regardless of weather fluctuations. This transformation marks the birth of the snow grooming industry, an entire sector devoted to shaping raw snow into perfectly controlled recreational terrain. The modern tubing hill begins with snow creation. While natural snowfall plays a role, most tubing parks rely heavily on artificial snowmaking systems to guarantee consistent coverage throughout the season. High-powered snow guns spray micro-droplets of water into freezing air, instantly crystallizing into fine snow particles that blanket the hillside. These systems can generate thousands of cubic feet of snow per hour, creating massive piles that form the raw material for grooming operations. As snow accumulates, bulldozers and snowcats push it into strategic locations, forming reserve mounds that will later be shaped into precise tubing lanes. Operators monitor snow depth, moisture content, and surface density to maintain ideal sliding conditions. This process continues day and night, often beginning long before the first visitor arrives. Once enough snow has been generated or accumulated, the true transformation begins. Specialized grooming machines, known as snowcats or snow groomers, move into action. These powerful vehicles are equipped with massive blades, tillers, and compaction systems capable of reshaping thousands of tons of snow every hour. Operators maneuver these machines across the slope, spreading out large snow piles and redistributing them evenly across the tubing hill. blades carve, smooth, and contour the snow, eliminating bumps and creating perfectly uniform lanes. Behind the groomers, rotating tillers break down larger snow chunks, producing a fine, consistent surface texture. This ensures smooth sliding, controlled speed, and reduced friction variation from one ride to the next. Under the glow of floodlights or moonlight, these machines operate relentlessly, shaping the slope into a winter highway of pure precision. The perfect tubing hill must meet specific engineering criteria. Slope angles are carefully calculated to deliver excitement without compromising safety. Too steep, and speeds become dangerous. Too shallow, and the thrill disappears. Laser leveling systems and GPS mapping assist operators in maintaining consistent gradients. Sensors measure snow depth and surface hardness, allowing teams to fine-tune conditions in real time. Snow is compacted layer by layer to create a stable base, then topped with a softer surface coat that provides optimal glide. This balance ensures riders move smoothly while maintaining control throughout the descent. This level of surface engineering transforms simple snow into a controlled recreational science. While visitors sleep, the snow grooming teams intensify their efforts. Night grooming is critical, as cold temperatures allow snow to settle and compact more efficiently. Machines run continuously, restoring worn surfaces after a full day of tubing activity. Tracks left by hundreds of riders are erased, and fresh layers of snow are redistributed to maintain consistent quality. This cycle repeats daily, ensuring guests wake up to perfectly prepared slopes each morning. The hill is not just maintained, it is reborn every night. Engineers continuously inspect tubing hills for hazards such as ice patches, uneven terrain, or debris. Protective barriers line the edges, while lane dividers guide riders safely down predetermined paths. Speed control zones and run-out areas ensure riders come to a safe stop at the bottom. Every element is designed with human enjoyment and protection in mind. Tubing parks generate millions of dollars annually. They create seasonal jobs, boost tourism, and support local economies. The snow grooming process itself represents a critical investment in maintaining customer satisfaction and safety standards. This industry fuels an entire ecosystem of equipment manufacturers, maintenance crews, and winter sports professionals. If you enjoyed this deep dive into one of America's most fascinating seasonal operations, don't forget to like, subscribe, and hit the bell for more behind-the-scenes explorations. Every day across America's heartland, a hidden giant is at work, mixing, blending, and balancing billions of pounds of grain, corn, soy, and minerals. All for one purpose: to feed the nation's cattle, the backbone of America's food supply. This is the story of the supergiant feed mixer plants, where technology, engineering, and agriculture meet on a breathtaking scale. From towering silos to roaring conveyors, from micronutrient dosing to precision blending, we'll see how science turns raw crops into perfect feed, enough to nourish millions of animals every single day. Before a steak reaches the dinner table or a glass of milk fills your fridge, it begins here, in the massive feed mills that power the cattle industry. These plants are engineering marvels. Each one can process over 1 million tons of feed per year, running 24 hours a day, 7 days a week. But why do we need such scale? Because America's cattle industry is enormous, more than 90 million head of cattle. each requiring a carefully balanced diet for health, growth, and production. From family farms in Texas to feedlots in Kansas, the demand never stops. So the feed mills must keep running, precisely, efficiently, and safely. The journey starts in America's fields. Vast oceans of corn, soybeans, wheat, and barley. Farmers deliver their harvest to the feed plant, where trucks line up like a moving river of grain. Each truck can carry up to 40 tons of raw ingredients. When the grain arrives, it's tested immediately. Technicians measure moisture, protein, and purity. Every batch must meet strict nutritional standards. Once approved, the grain flows into towering storage silos, some over 150 feet tall, each holding thousands of tons of material. From above, the feed plant looks like a futuristic city. Pipes, elevators, and conveyors linking dozens of towers into one synchronized machine. Now comes the transformation. Massive hammer mills, some the size of shipping containers, grind corn and soybeans into fine meal. The goal: uniform particle size for better digestion and nutrient absorption. Each mill can crush up to 50 tons per hour, generating thunderous sound and clouds of grain dust. But inside the control room, operators monitor everything through digital screens, adjusting temperature, airflow, and grinding speed in real time. Next, the ground meal moves to the mixing chambers, enormous horizontal blenders that can hold 20,000 pounds of feed at once. Here, computer systems take over. Dozens of silos release ingredients in exact proportions: corn, soybean meal, vitamins, minerals, fats, and sometimes probiotics. Each recipe is calculated down to the gram, ensuring the cattle get the right nutrients for their age, breed, and purpose, whether it's dairy production or beef finishing. Feed mixing isn't guesswork, it's agricultural science. Inside every plant is a nutrition lab, where scientists test samples for energy, protein, fiber, and moisture. They run spectrometer scans, compare readings, and adjust formulas daily based on cattle health data. In the past, feed was mixed by hand and intuition. Today, algorithms and data analytics decide the balance. For example, a typical beef formula might include 60% corn, 20% soybean meal, 10% roughage, and 10% supplement mix. All optimized for weight gain and feed efficiency. The result? Healthier cattle, less waste, and lower costs for farmers. Walk inside a super feed plant and you'll see some of the largest moving machines in agriculture. Gigantic conveyors stretch hundreds of feet, carrying tons of feed per minute. Massive mixers rotate with slow, deliberate power, like industrial hearts beating in rhythm. Dust collectors, air filters, and cooling fans keep the environment safe and controlled. At the top of the system, computer screens flash with color-coded indicators, every motor, belt, and auger under constant surveillance. If one machine stops, the whole process can pause. That's why redundancy systems, backup motors, emergency silos, and remote controls are always in place. Not all feed stays as powder. In fact, most of it becomes pellets, small dense cylinders that are easier to transport and store. The pelleting line is one of the most fascinating parts of the process. The blended meal is steamed at 180-degree Fahrenheit, softening starches. Then, it's pushed through steel dies that compress it into uniform pellets. These pellets are cooled, screened, and tested for hardness. Too soft, they crumble. Too hard, cattle won't eat them. It's precision down to the millimeter. Each pellet contains everything the animal needs: energy, protein, fiber, vitamins, in one perfect bite. Once cooled, the feed is ready to move. Bulk loaders fill massive semi-trailers bound for ranches and feedlots across the Midwest. Each trailer carries enough feed for hundreds of cattle. GPS tracking ensures every shipment arrives on time. For smaller farms, automated bagging lines fill and seal 50-pound sacks, stacking them onto pallets by robotic arms. It's a dance of logistics and precision, every hour, every day. From the golden fields of the Midwest to the shining steel of America's superfeed plants, every step of this journey tells one story. The story of how human ingenuity feeds the future. If you enjoyed this deep dive into the hidden world of feed production, hit that like button, subscribe, and ring the bell, because more incredible stories of science, industry, and life are coming your way. These turbines are more than just modern landmarks. They're part of America's clean energy revolution. And at the heart of this revolution lies one of the most mind-blowing feats of engineering and manufacturing: the creation of wind turbine blades that are longer than the wings of a Boeing 747. Today, we're going inside a supergiant wind turbine plant to uncover the jaw-dropping process of how these massive blades are designed, built, and prepared to withstand decades of storms, winds, and weather. But before we dive in, don't forget to subscribe, hit the like button, and ring the notification bell so you never miss more behind-the-scenes journeys into the world's most incredible industries. To understand the scale of wind turbine blade manufacturing, let's first look at the turbines themselves. The average onshore wind turbine today stands about 300 feet tall, with blades stretching over 200 feet long. Offshore turbines are even larger, some reaching over 850 feet tall, with blades exceeding 350 feet in length. That's longer than the wingspan of most passenger planes and nearly the length of a football field. Why so big? The longer the blade, the more wind it can capture, and the more energy the turbine can generate. A single modern turbine can power up to 2,000 homes per year, and offshore giants can supply even more. But building something that large isn't easy. Blades must be both incredibly strong to withstand hurricane-force winds and remarkably light so they can rotate efficiently. Achieving that balance requires advanced materials, state-of-the-art facilities, and a manufacturing process that feels closer to building spacecraft than farm equipment. Before a single mold is made, engineers spend years perfecting blade design. Aerodynamics is everything. The shape of a blade is similar to an airplane wing, with a curved surface on one side and a flatter surface on the other. As wind flows over it, lift is generated, causing the blade to spin. But it's not just about performance. Blades must survive 20 to 25 years in the harshest conditions: freezing winters, blazing summers, salt spray from oceans, and winds that change direction in an instant. That's why the materials chosen are just as important as the design itself. Once the design is finalized, production begins with the creation of a massive mold. Think of it like baking a giant loaf of bread. You need the right mold to shape it. Except in this case, the mold is the size of a football field. Each blade requires 2 molds, one for the top half and one for the bottom half. These molds are precision engineered out of steel or advanced composites, with heating systems built into their structure to cure the materials evenly. Workers climb ladders and scaffolding to apply layers of coating inside, ensuring a perfectly smooth finish that will shape the final blade's aerodynamic surface. The backbone of wind turbine blades is fiberglass. Huge sheets of woven fiberglass fabric are laid carefully inside the mold, layer after layer. In high-stress areas, like the root where the blade connects to the hub, engineers often reinforce the structure with carbon fiber, which is lighter and stronger than steel. This process is called lamination, and it requires precision. Too little fiberglass and the blade will crack under stress. Too much, and the blade becomes too heavy to turn efficiently. Workers, often in teams of dozens, lay down these sheets like tailors sewing fabric, making sure every piece overlaps perfectly.